Video is the third in Unit 9. Continuing on with solids, and this video will cover molecular solids briefly and then get into a little bit of the ionic solids. Now, I wanted to include the molecular solids on this video, even though we have talked about intermolecular forces, which really includes molecular solids because we're talking about covalent molecules. And covalent molecules sometimes have somewhat of a lattice structure, but keep in mind it's only because covalent molecules can also be ions. So they have very, very strong bonds inside the molecule, but really weak interactions outside the molecule. So some common examples would be ice, dry ice, carbon dioxide, sulfur, because it bonds to itself in a rhombic, in a S8, and phosphorus, P4. So we see, again, large molecular units that can all be attached together like ice because water will attract itself, but there are individual small molecules within that, but they can just build really large structures without being completely bonded together. There are some different atomic separations within the molecules in terms of distances. Again, nothing that I'm going to probably test you on, but just to kind of take a look here, the closest distance between the molecules in the substance is far different and far larger than the distance you see within the atoms within the molecule. So again, that has a lot to do with the strength, right? As we know that the closer these attractions can get, the stronger they are. And so these are nearly double, and that's part of the reason why we see a dramatic difference in the strengths. So keep in mind when molecular solids are polar, they have something called a dipole moment, and this is when we see things like dipole-dipole interactions, which are in the middle of the road. If you remember, hydrogen bonding was kind of a turbocharged version of dipole-dipole. Definitely stronger. So hydrogen bonding is the strongest intermolecular force, then dipole-dipole, and then our last is London dispersion forces. So water, as we spoke about earlier, not only has polar bonds, it has a dipole moment, but it also has hydrogen bonds. And this is why we see something really cool in water that we don't necessarily see in other things. So hopefully that's a little bit of a review, but just to remind you, since we are talking about solids, I wanted to include that, even though we talked about intermolecular forces. Now, ionic solids are definitely different, and we see this lattice structure where we have cations and anions surrounding each other. They're extremely stable. They have very, very high melting points because this cation-anion ionic bond or really, really strong electrostatic attraction between them. It's really, really strong. And so I want you to think about this for a second. When I boil something covalent, so when I boil water, I'm not breaking a bond. We've talked about this. I'm only breaking the intermolecular attraction between the water molecules. When I boil an ionic solid, I am truly breaking a bond. I am breaking sodium from chlorine when I do that. So when I melt that, I am breaking the bond between them. So something to kind of think about, and this is why we see such incredible high melting points from them, because we're breaking bonds in this case. So most binary ionic solids, so we have one cation, one anion, they're typically packed in a closest packed arrangement, very much like our metallic solids. So we see hexagonal closest packed and cubic closest packed arrangements, just like we saw in our metallic structures. The smaller cation fits into the tiny little holes that are left after they're in this closest packed arrangement. So that's, of course, to maximize those electrostatic attractions between them. So what we see here are three different types of little holes that we'll see in these cubic and hexagonal closest packed arrangements. The smallest one is a trigonal hole, and it's when it's planar, so these three atoms are flat, and I have this tiny little hole there. That's normally not big enough for any of our cations to actually fit in. The second one, the tetrahedral holes, again, this is when I add this third dimension. So I now have 4 atoms here, and the hole in between here, because this is a tetrahedral, This is the second largest hole, and again, for the most part, not large enough to put in a cation. But once I add my 6 atoms, so I have an octahedral, and yes, I know octahedral means 8, but if you think about the shape that this would take in the faces, the number of faces it would have, just like the octahedral shape in molecules, the 6 atoms create this 8-faced shape. The space that is in there is big enough to hold a cation. And so this repeating structure, sometimes the octahedral holes are filled, sometimes they're not. It depends on the ratio of cations to anions. But this is how we kind of get those things all kind of packed in there. So the holes increase in size from trigonal, tetrahedral to octahedral. And like I said, trigonal ones don't normally hold anything. The tetrahedrals do on occasion, but the octahedrals are normally the ones that hold it. So I know this was an example problem, and I already have the answers here. But we have some of these practice problems in the book, and I would highly encourage you, if you have any question about your ability to look at something and go, yes, I know this is a metal, and therefore it's going to have metallic bonds, and it's a metallic solid. This is covalent, and we know it's covalent because it's a nonmetal and a nonmetal bonded together. So a covalent molecule is considered a molecular solid. This is a cation and anion, and an ionic solid. And finally, krypton. This is our 8A, or our noble gases. So you're going to see a few of these on your quizzes and tests. I would highly recommend that you take a good look at it. There is a summary table, 10.7. Even though this is Unit 9, this is Chapter 10 for the most part. And this is a really good summary of all of our solids. If we look, we have ionic, molecular, and then atomic solids are actually split into 3 subcategories. Network, because I have carbon and silicon as our basis for that. Then our metallics, so any single metallic element would make a metallic solid. And group 8A, the weakest of all of them, and these are our noble gases. And that is the end of the solids. I have another video coming up for vapor pressure and some phase changes. And please let me know if you have any questions, as usual.